In this video, what I'd like to do is examine the relationship between the first and the second derivative as it relates to their sign and the graph of the original function. What I have here is a third degree function, f, and some notable points. I first identified a point A and a point C. As you'll probably recognize, the value of the derivative at the points A and C are equal to 0. On the interval negative infinity up to a, we know that that first derivative, the original function is increasing, so the sign of that first derivative is going to be positive on that interval. And then from the point A to C, the function is decreasing, and so we know that the sign of the first derivative is going to be negative on that particular interval. And then it's going to be increasing, and so it's going to switch over to positive on its way to infinity. We know, of course, by our first derivative test that we have a maximum value at x equal to a, and we have a minimum value at x equal to c. And that's all from the previous section in which we examined the first derivative and we were given the first derivative test. As we take a look at the second derivative, in this particular graph, I've identified a third point, B, and this is a point in which we have a change in concavity. The function begins by being concave down. Sometimes we refer to concavity as holding water or losing water, and it is concave and it's in a downward direction. So if you were to put water in this area, it would actually fall out. So it's concave down. Whereas here, if you put water in here, it would actually collect water. It's concave up. And B is a point where we have a change in concavity. In this particular graph, we're going to have a point where the second derivative is equal to 0. And since it's concave down, what we have is a negative value on our second derivative. And then where it's concave up, it's a positive value on that second derivative. And so, once again, just as we look at the relationship here, the definition of our concavity is a function is concave down when its derivative is decreasing. And what we have here is the derivative is decreasing because the second derivative is the derivative of the first derivative. And since that second derivative is negative, we know that the first derivative is actually decreasing from left to right on this interval, from negative infinity to b. The value of the first derivative is decreasing, so it is concave down. And then since the second derivative is positive, we know that the first derivative is increasing on that interval. And so this is a value where the second derivative is equal to 0. We refer to it as an inflection point because we have a change in concavity. Okay, and that's part of our definition. If there is a change in concavity and we have a second derivative equal to 0 or undefined, we have an inflection point. And of course it has to be defined on the original function for the original interval. So just to take a look at our conclusions here, we know that f increases on negative infinity to a union c to a positive infinity. We know that f decreases on a to c. We know that f is concave down on a negative infinity to b. F is concave up on b to a positive infinity. Just another interesting thing to note as we take a look at the second derivative test is that if we evaluate the second derivative at these points, you'll note that f double prime of a is actually less than 0. And since it's concave down, we can conclude that it's a maximum. For concave down, we're going to have a maximum value there because it's concave down. And noting here, f double prime of c is greater than 0, well, that gives us a minimum because we know it's concave up. So if we have a critical number and we plug it into the second derivative and we have a value where the second derivative is positive, making that concave up, we know it's a minimum. Whereas if it's if the second derivative's value is negative, we know it's concave down, and so we'll have a maximum. And so as part of our conclusion, we can also say that f has a relative min at x equal to c and a relative max at x equal to a.